Hey everyone, Mr. Andrew here. Today I wanted to talk to you about Lewis dot structures and how we use them to depict the formation of ionic compounds. Now, previously we've talked about Lewis dot structures. Lewis dot structures, as you recall, are the atomic symbols with dots around them to show how many valence electrons an atom has. Well, we can use Lewis dot structures to show how electrons are transferred between different atoms to form new ions and therefore new ionic compounds. Let me show you what I mean. So this first question right here says, use Lewis dot structures to show an ionic compound formed between sodium and chlorine. So the first thing I'm going to do is I'm going to draw the Lewis dot structure for sodium and for chlorine. So for sodium, it's just Na. Sodium has one valence electron, so it just has one dot. Okay. Chlorine, on the other hand, is Cl. And chlorine has 7 valence electrons, so I'm going to put 7 dots around it. 1, 2, 3, 4, 5, 6, 7. Okay, so we've got the two Lewis dot structures. Now, chlorine has an open spot for a valence electron. Sodium wants to lose its valence electron, so this electron is going to go right here on chlorine. And as a result of this, after the reaction is done, what we're going to end up with is a sodium, which has a positive charge, and a chlorine, as I said, a chlorine, which now has 8 new valence electrons around it. And it's going to have a minus charge. Now, a couple things about this, okay? Sodium is now positive because it lost its valence electron, and chlorine is negative because it gained a valence electron. Also, the Lewis dot structure for sodium is shown with 0 valence electrons, but that's not necessarily true. What it's showing you is that what was originally the outermost shell of sodium is now completely empty. Okay? Now, that doesn't mean it doesn't have valence electrons now. Remember, it's gone to one energy level lower. It's mimicking the noble gas from the period before it. But in what was originally its outermost shell, it now has no valence electrons. Okay? So this whole thing right here is how you would depict the formation of an ionic compound formed between sodium and chlorine. And as we can see, they're neutrally charged. There's one positive and one minus, so they're going to cancel each other out. Now, here's one thing that you may see sometimes, and it's something that I like to do, okay? See, because the dots from both sodium and chlorine are valence electrons, it becomes hard to tell in the end product where these electrons came from. So what I like to do, and what you will see sometimes, I'm just going to redo the problem real quick. Oop, I didn't want to do that yet. Sodium, I'm going to keep the dot the same. Okay, but for chlorine, I'm going to replace the dots with X's. Okay. Now remember, these are just kind of representations of electrons. As long as I am clear that these X's are also valence electrons, they're just valence electrons from this different atom, then it's totally fine, okay? So this electron goes right here, and as a result, we have sodium plus, and we have chlorine, chlorine minus. Now you see how you can easily tell where that valence electron came from? This dot right here is even though it's a different representation, it's still a valence electron. So we can clearly see chlorine originally had 7 valence electrons, and then it gains 1 more from sodium to become 8. Both of these are correct. You could see it either way. I prefer this second method, but if you want to do the other method, this first method, that is totally fine too. And many people will consider that to be kind of the mainstream way of doing it. Okay? So let's look at the next one. It says, use Lewis dot structures to show an ionic compound formed between potassium and oxygen. Okay? So here's what we're going to do. I'm going to draw the Lewis dot structure for potassium. Okay, put a dot right there. Draw the Lewis dot structure for oxygen. Okay, I like the X method, so I'm going to go ahead and do that. Okay, so potassium's got 1 valence electron and oxygen has 6. Okay, now we have a minor problem here. Okay, and that minor problem is that potassium, 1 potassium alone, is not enough to fill up the valence shell of oxygen. Okay. Now this is pretty easily solved if we use the crisscross method, right? We put K, we put O, potassium's 1 plus, oxygen's 2 minus, crisscross, and we're going to end up with K2O. So I know I'm going to need 2 potassiums. So I'm going to go ahead and add another one here. Okay. Now I'm going to show how those electrons are transferred over. And as a result of this reaction, I end up with 2 potassium ions and 1 oxygen. And that oxygen looks something like this. And that oxygen is going to have a 2 minus charge. So in this way, we're showing that these positively charged potassiums are attracted to the negatively charged oxygen. Okay. So let's keep going here. Okay. Now I'm going to keep working through these. Okay. And I'm going to pick up the pace a little bit because I have a lot to do and I don't want this video to be super long. So same thing, magnesium and sulfur. Magnesium has 2 valence electrons. Sulfur has 6. So these 2 electrons are just going to fit in the spots right here. And we're going to end up with Mg2 plus and sulfur two minus. So we're just showing how these electrons are moving. Okay. Next one, aluminum. Aluminum has 3. Okay. Now I'm arranging these electrons in a way that makes it easier for me to draw this out. And you're allowed to do that as long as you follow the rules. You have to have 1 on each side before you pair. But it doesn't matter what side the electrons go on as long as they follow the rules. So I've got an aluminum, I've got a nitrogen. Okay. So I'm going to do something like this. So I put the pair on the other side so that way it's easier to draw this out. But these electrons are going to move like this. And I'm going to end up with aluminum 3 plus and nitrogen dot x x x x dot x dot. So see, this is what I like about this method is I can clearly see where aluminum's electrons went and where nitrogen's electrons just kind of stayed there. Okay. All right, let's keep going on. Now these are the same problems you're going to have in your notes. So use this video to help you refresh your memory if you get to the point in your notes where you're wondering kind of what's going on, okay? Use Lewis dot structures to show the ionic compound formed between strontium and phosphorus. Okay, now this one is a little bit more complicated because strontium has 2 valence electrons and phosphorus has 5. Okay, so if we do the crisscross method, what we're going to end up with is SR3P2. So I need more strontiums. And I need more phosphoruses. Okay. And now I'm just going to use these electrons to fill in the gaps. This one's going to go here. 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 And this one's going to go here. So what we're going to end up with is SR2 plus, SR2 plus, SR2 plus, phosphorus, X dot, X dot, X. That's 3 plus. Okay, so this whole contraption right here, this is our new ionic compound, where the 3 strontiums have given up their electrons to these 2 phosphoruses to kind of stick everything together. Okay, so similar one over here. Okay, the difference is gallium has 3 valence electrons and selenium has 6. Let me switch those to X's so that way we're keeping consistent with what I've been showing you. Okay. Crisscross method. It's going to be Ga2Se3. Okay, so I need 2 galliums and 3 seleniums. It's a little too close. Okay, so this one's going to go here. This one's going to go here. This one right there. This one right there. This one right here. This one right here. What we're going to end up with is 2 galliums, each with no dots showing, and they're each going to be 3 plus. And then 3 seleniums. 1, 2, 3, 4, 5, 6. Fill in the dots. 2 minus. 2 minus. So you can see how the electrons are moving from gallium here over to selenium. Okay. Okay, now the 3 that I've got for you to do on your own. Okay, so first one, we're doing beryllium and oxygen. Okay, so beryllium has 2. I can make that dot look a little bit nicer. And oxygen has 6. something like that. So we end up with Be 2 plus, and oxygen 2, 3, 4, 5, 6, dot, dot. And that's a 2 minus, okay? It's a very straightforward skill once you figure out how it works. So you're just drawing the two structures, showing how the electrons move, and then making sure that they're balanced, okay? Okay, rubidium and nitrogen. So rubidium has 1, nitrogen has 1, 2, 3, 4, 5, okay? So this is Rb 1 plus, nitrogen 3 minus, crisscross, Rb3n is going to be my correct formula. So I need 3 rubidiums here. So I'm going to add 2 more. Okay. Put the electrons in the correct spots. And we're going to end up with okay, so these 3 rubidiums lose their electrons, and this 1 nitrogen dot x dot x dot. Okay. So again, this is our final answer right here. Okay. Okay, last one, aluminum and oxygen. Okay. So aluminum has 3, oxygen has 6, crisscross method, Al3 plus, oxygen 2 minus, okay, you end up with Al2O3. So we need 2 aluminums and 3 oxygens. Okay. Okay. So aluminum's electrons fill all those gaps. So oxygens all now have complete octets. We're going to have 2 aluminum cations with a 3 plus charge. And we're going to have 3 oxygens. Each one is going to have a newly filled octet. And each one is going to have a 2 minus charge.